Chapter 2, Circuit Elements. In this lecture, we will define resistance, the resistor, the symbol for the resistor, and the behavior of an ideal resistor. We will introduce Ohm's Law and the associated equations, and how it relates voltage, current, and resistance. Lastly, we will define conductance and show how it can be used in an alternative expression for Ohm's Law. The learning objective that we are looking at two learning objectives. One, to understand the symbols for and the behavior of the following ideal basic circuit elements. In this lecture, we will be looking at the resistor. We will state Ohm's Law in this lecture. Resistance is the capacity of materials to impede the flow of current, or more specifically, the flow of electric charge. When current flows in conductors, electrons, which make up the current, collide with the lattice of atoms in the conductor. This impedes or resists the motion of the electrons. The larger the number of collisions, the greater the resistance in the conductor. The circuit element that models this behavior is the resistor. Some metals with small values of resistance are copper and aluminum. These metals are used for wires. So the wires and circuits do have a small resistance, but we do not consider this resistance in circuit analysis. Many materials closely approximate the ideal linear resistor. Metals used for resistors would be metallic alloys and carbon compounds. Resistors are the simplest and most commonly used circuit element. The value for resistance is denoted by the symbol capital R, and the SI unit to measure resistance is the ohm. Ideal resistors model the behavior of physical devices. The word ideal indicates that the resistor model makes several simplifying assumptions about the behavior of actual resistive devices. The most important simplification is assuming that the resistance value does not vary over time. Most resistive devices do have a time-varying resistance, often because the temperature of the device changes over time. The ideal resistor model has a value which doesn't vary much from the constant value over the time period of interest. Let's take a closer look at the resistor. Resistors that we will be using in the lab have a color code. Black is 0. Let me get the laser here. Black has a value of 0. Brown has a value of 1. Red has a value of 2, etc. You will notice that resistors have bands of color. The first and second bands are the first and second figures of the value. The third band is a multiplier, and the fourth band is the tolerance value. You can see some examples here. For instance, this resistor has a brown band, followed by a green band, followed by an orange. The brown has a value of 1, green has a value of 5, and orange has a value of 3. So this would be 15 times 10 to the 3, or 15K ohm. The last band is a tolerance value. In this case, it's gold, which means that the tolerance is plus or minus 5%. So this resistor is guaranteed to operate 15 within to resist 15K ohms plus or minus 5%. Let's do one of our own here. Let's say, oh, you know what? Let's draw a resistor here and have it look something like this. And let's give it a red band. Oh dear, that's terrible. Followed by, how about a green band? That's a little better. And let's do a violet band. And I'm going to go with gold. And unfortunately, I don't have gold here, but pretend that this is gold. It's really orange. Let's add some yellow to it. Maybe it'll help it look gold. We're going to pretend that's gold. All right, so we have this resistor. And so red has a value of 2. Green has a value of 5. And violet has a value of 7. So our resistor value is 25 times 10 to the 7. And this gold would be plus or minus 5%. Okay, so this would be 250 mega ohm, right? Now, the plus or minus 5% tells us that our resistor will operate within the range of plus 5% would bring it to 267.5 mega ohm. Minus 5% would bring it to 237.5 mega ohm. And that's the operating range for that resistor. Okay. Let's look at the terminal relations of a resistor based on Ohm's law. Ohm's law states that the voltage across conducting material is directly proportional to the current flowing through the conducting material. We can say this mathematically as V is equal to IR, where V is the voltage in volts, I is the current in amperes, and R is the resistance in ohms. So since voltage is directly proportional to current flow, and current flow is directly proportional to the voltage, as voltage increases, current will increase. If voltage increases by double, current will increase by double. If voltage decreases by half, current will decrease by half. Okay, let's rewrite the equation to V equals Ri. In this equation, we have a straight line where R is the slope. So we have a straight line here, and the slope is the change in current. Well, it's rise over run, so it's change in voltage divided by the change in current, and that is equal to R. Since we have a straight line, we will say that our resistor is linear or ideal. Let's talk about conductance. Conductance is the reciprocal of resistance. The symbol for conductance is the capital G, and the SI unit is Siemens. Mho is the former unit for conductance, which is ohm backwards. Conductance offers us an alternative expression for Ohm's law. So V would be I over G, or current is equal to conductance times voltage. Let's review the topics that we have covered in this lecture. We defined resistance, the resistor, the symbol for the resistor, capital R, and the behavior of an ideal resistor. We introduced Ohm's law, the associated equations, and the relationship between voltage, current, and resistance. And lastly, we defined conductance and the symbol used, as well as how it can be used in an alternative expression for Ohm's law. And this concludes this lecture.